So let's jump right in. First up, what really happens when a star dies? It's a terrifying but honestly fascinating question, right? Because that's where these cosmic monsters actually come from. We usually look up at the night sky and kind of think of stars as permanent fixtures, but they all have a life cycle. And for some of them, the end of that life cycle is incredibly violent.
That brings us to Section 1, Birth of a Monster. We're going to begin our spatial journey from a nice, safe distance, just observing the violent end of a massive star's life cycle.
So look at what happens here. Once a star exhausts its internal fuel, gravity just completely takes over. For billions of years, a star survives by fusing elements in its core, and that creates this massive outward pressure that perfectly balances the crushing inward pull of its own gravity. But when that fuel finally runs out, it just can't support its own weight anymore. Gravity suddenly wins the ultimate tug of war, and the core collapses inward at staggering, mind-bending speeds. But there are strict mass thresholds for this collapse, which you can see mapped out here. Not every dying star actually turns into a black hole. While a star like our Sun will eventually just compress into a small, stable white dwarf, heavier stars, we're talking between 8 and 25 solar masses, they'll collapse into incredibly dense neutron stars. But the absolute giants, the stars over 25 solar masses, they experience a collapse so catastrophic that literally no force in the universe can stop it. They collapse entirely into black holes. Moving right along to Section 2, the accretion disk. As we get a bit closer on our journey, we encounter this brilliant, chaotic halo surrounding the darkness. Imagine you're in a spacecraft, safely approaching a black hole. Ironically, the very first thing you'd notice is incredibly bright light. It's actually a really common misconception that black holes are just entirely invisible. While the hole itself doesn't emit any light, the environment immediately surrounding and actively feeding black hole, it's home to some of the brightest phenomena in the universe. Let's break down how this brilliant halo actually builds up. Because of the conservation of angular momentum, gas and matter falling toward the black hole don't just, drop straight down. First, the gas gets trapped in a flattened orbital disk. Then, within this disk, the particles aggressively rub and bounce against each other in this crazy turbulent flow. This immense friction generates massive heat, bumping the temperature up to millions of degrees. And finally, blinding electromagnetic radiation, specifically X-rays, are emitted. And actually, fun fact, this X-ray emission is exactly how astronomers detect a lot of black holes hiding out in the dark. All right, Section 3, busting the vacuum myth. Before our imaginary spacecraft gets dangerously close, we really need to correct the record on a wildly popular sci-fi misconception. The myth is that black holes are cosmic vacuum cleaners. But the absolute fundamental fact here is that they do not simply suck everything in. As long as you stay far enough away, their gravity is absolutely no different than a star of the exact same mass. You could happily orbit a black hole forever, just like planets orbit regular stars. To really put that into perspective, think about this thought experiment. If our sun suddenly collapsed into a black hole of the exact same mass right now, we would definitely freeze in the pitch black, which, wouldn't be great for our weekend plans, but our orbital path wouldn't change one single bit. Earth would keep moving around that black hole in the exact same path it travels today. The danger only arises when you get too close. And speaking of getting too close, here's Section 4, crossing the event horizon. As our spacecraft pushes further inward, ignoring all common sense, we finally hit the ultimate boundary. The official physics term for this boundary is the Schwarzschild radius. This perfectly dictates the distance from the very center of the black hole all the way out to its event horizon, literally the point of no return. And as you'd probably guess, the larger the mass of the black hole, the larger this radius extends. It helps to think of that warped space-time boundary kind of like the edge of a deep, dark well. Cross this event horizon, and the escape velocity required to leave the black hole actually exceeds the speed of light. And since nothing in the universe can travel faster than light, once you slip past this edge, that's it. No signal, no light, and no physical object can ever climb back out. Now, you might think crossing this line means instant spaghettification, which, by the way, is a completely real, albeit delicious-sounding, physics term for when gravity stretches you into a thin string of atoms. But whether you spaghettify right at the horizon actually depends entirely on the black hole's size. If you were falling into a massive city-sized stellar black hole, you'd be torn apart before you even reached the edge. But if you were falling into a supermassive black hole, like the ones at the center of a galaxy, the distance to the singularity is so vast that you might actually drift past the event horizon completely unharmed. You might not even realize your doom until you get much, much deeper inside. Which brings us to Section 5, the ultimate paradox. We are now in free fall toward the very center, where our entire understanding of physics completely shatters. We inevitably hit the singularity. This is a mathematically terrifying concept, honestly. At this exact center, all the massive amounts of matter from that dead star we talked about earlier is crushed into an infinitely small, infinitely dense point. Space and time, as we understand them, just oscillate chaotically and cease to have any meaning at all. General relativity totally breaks down. But here is where it gets even weirder. Stephen Hawking realized that black holes aren't actually permanent cosmic traps. He discovered that due to complex quantum effects near the event horizon, black holes aren't entirely black. They actually leak a tiny, tiny amount of thermal energy, known as Hawking radiation. Over an unimaginably long timescale, we're talking billions upon billions of years, they slowly leak this energy until they completely evaporate into nothingness. Now, this presents a massive problem. If a black hole completely evaporates and just disappears, what happens to the physical information of everything that ever fell inside it? Say you threw a book in there. As physicist Leonard Susskind pointed out, if the unique quantum information of that book is truly lost forever, it would violate unitarity. Unitarity is a bedrock principle of quantum mechanics which strictly insists that information can never, ever be permanently lost from the universe. And that leaves us with a mind-bending crisis, the black hole information paradox. Is the universe's data simply lost forever when the black hole evaporates, meaning quantum mechanics is broken? Or, as some theorists suggest, does an undetectable, violent wall of fire sit right at the event horizon, instantly incinerating everything to protect the laws of physics? If that's true, it would mean Einstein's theories of general relativity are broken. We are still desperately searching for the answer. So, what do you think? Will quantum mechanics or relativity have to give way to solve the ultimate mystery of the abyss?